Welcome back to Very Ordinary Differential Equations. In this lecture, we begin learning about the Laplace transform. First, what is the Laplace transform? So suppose you have a function f of x, which is integrable on any interval of the form 0 to t, where t is a positive number. That is, if I integrate from 0 to capital T of f of x, that integral exists. Even if there's no obvious way of computing its actual value, if you just know it exists, that's good enough. So for example, if f is piecewise continuous or even just piecewise monotone on the non-negative real numbers, then this property holds. So if you have a function which is integrable on any interval from 0 to t, you define the Laplace transform to be the function capital F, defined as capital F of s is this improper integral from 0 to infinity, where here you have f of t dt, multiplied by e to the minus st. Okay, now by definition, this improper integral is a limit as t goes to infinity of this proper definite integral. Notice that we have capital F of s, a new variable, which only appears in the exponential term e to the minus st. So here is our definition of the Laplace transform. Capital F of s is the integral from 0 to infinity of e to the minus st, f of t dt. So we define capital F in this way, provided that this improper integral converges. Now, s is the variable of the function capital F. However, within the integral on the right, it acts as a constant. The variable of integration on the right is t. S is a constant that only appears in the exponent there. If this improper integral converges for some choice of s naught, then it will converge for any value of s bigger than or equal to s naught. So if you can ever show that this improper integral converges for a specific choice of s, it will automatically converge for any larger choice. So therefore, the domain of this function capital F could be empty. Maybe this improper integral never converges. Maybe it converges for all real numbers, or perhaps it converges for some interval of this form. Either including a or not, it's a little ambiguous, but once it converges for some number, it will automatically converge for all numbers larger. Let's denote L of f by the Laplace transform of little f. So for any two functions f and g and any two real numbers a and b, the Laplace transform acts as a linear operator on functions. In other words, the Laplace transform of af plus bg is equal to a times the Laplace transform of f plus b times the Laplace transform of g. So it's a linear operator on a space of functions. We'll see why this property, linearity, is so incredibly useful. The proof that the Laplace transform is linear is not really very complicated. Integration is also linear. The integral of f plus g is the integral of f plus the integral of g, and constants also factor out. And the Laplacian operator is fundamentally defined through integration, so that's basically the proof right there. Now we're going to introduce a little notational convenience. This is assuming that we're all quite comfortable computing improper integrals. So generally what we would need to do is two separate steps. First, compute the definite integral from 0 to capital T of e to the minus st f of t dt. And then you would need to take a limit as t goes to infinity. But we're really just going to do both of those at once, again, assuming that we have all done many of these improper integrals before, so this is not really worth writing out every time. So for example, suppose we take the easiest function we can. Little f of t is just the constant 1. Then we would just write the improper integral of e to the minus st times 1. Well, integrating this will just be e to the minus st over s. Remember, in this integral, the variable is t, and s is a constant. So I have e to the negative constant t. Antiderivative is negative e to that over the constant s. Evaluated in big air quotes at infinity and 0, well, as this upper limit goes to infinity, e to the negative infinity collapses down to 0. So we would get a 0 here, minus evaluating this at 0. If this exponent is 0, then we have e to the 0 is 1. So this becomes a plus 1 over s. So we're not writing out this definite integral followed by a limit. We're just kind of absorbing that all into one step here. And again, this assumes that we have all done many of these improper integrals before. So if you haven't worked through a lot of improper integrals before, you probably should. Also, don't make the mistake of thinking that we are plugging infinity into any function. We really are plugging in a capital T and taking a limit as capital T goes to infinity. Infinity is not a number. We can't plug it into a function. We're just saving some writing by using notation that suggests that's what we're doing. We're just suppressing writing out that limit over and over and over again. With that in mind, let's do an example. Compute the Laplace transform of the function we just did, f of t equals 1. So we compute capital F of s. So here, if we wanted to write out this limit, we would replace this improper integral with this limit of a proper definite integral. And now we've replaced f of t with 1. So we would take the limit as capital T goes to infinity. Here we have it. Remember, these variables refer to the variable of integration, which was little t. So first you plug in there, and then you plug in t equals 0. E to the 0 gives me a 1. As t goes to infinity, this collapses to 0, and we just get 1 over s. In the shorthand notation from the previous slide, it's what we did on the previous slide. We suppress writing out the limit every time because it's assumed we've all done it 50 to 500 times in our lives, and we can kind of skip over that. Note that we do have to assume s is not 0. If s is 0, then e to the minus st is always 1, and we would just be integrating the function 1, which is not integrable as this limit goes off to infinity. However, for any positive value of s, this does converge to 1 over s. So the domain of our Laplace transform capital F of s is positive values of s. As a second example, let's compute the Laplace transform of an exponential. F of t is e to the at for any choice of a. So we set up our integral. Capital F of s is the integral from 0 to infinity of e to the minus st f of t dt. Then we plug in our value. F of t is e to the at. We can combine these two exponentials into one term. So we have the improper integral, 0 to infinity, of e to the minus s minus a times t dt. Integrating this is fairly straightforward. S minus a is just a constant, okay? And again, plugging in the upper limit and letting that go to infinity, and then plugging in the lower limit of 0, works out to just be 1 over s minus a. And for which values of s does this actually converge? It does not converge for s equals a, but it will converge for any s larger than a. So the domain of this function is now all s larger than a. As our third example, compute the Laplace transform of this function. F of t is defined piecewise. For t less than 5, f of t is 0, but for t bigger than or equal to 5, f of t is 1. We can still compute the Laplacian even though we have this piecewise definition. Instead of integrating from 0 to infinity, e to the minus st f of t dt, since the function changes value at 5, first integrate from 0 to 5, and then integrate from 5 to infinity. Now from 0 to 5, the value of f of t is just 0, so that integral will just be 0. So all we really need to do is integrate from 5 to infinity e to the minus st. That's pretty straightforward. It's negative e to the minus st over s. We plug in our upper limit, take a limit as it goes to infinity, plug in the lower limit of 5, and we end up with exactly e to the minus 5s over s. And the domain here will be all s which are positive. So even though the function was piecewise defined, we could still quite directly compute the Laplace transform. This gives rise to something known as the shifting theorem, which will be very useful for us later. If capital F of s is the Laplace transform of f of t, defined for all s's past a certain point, then capital F of s minus a must be the Laplace transform of e to the at f of t. And the domain here is all s's larger than s naught plus a. In other words, if you can compute the Laplace transform of this function and you get capital F, then you can definitely compute the Laplace transform of this, and it will just be a horizontal shift of the same function, capital F. So if the Laplace transform of little f is capital F, the Laplace transform of e to the at f of t is capital F of s minus a. The proof is actually quite straightforward, so we're going to go ahead and include it. Capital F of s minus a, by definition, is the integral from 0 to infinity of e to the minus s minus a times t f of t dt. This is just the definition of the Laplace transform, but instead of s, it's s minus a. Properties of exponents work out quite nicely, however. This exponent, if I distributed, would give me a minus st plus at. So I have e to the minus st plus at, and I split that off as e to the at, f of t. So now what do I have? I have the integral from 0 to infinity of e to the minus st times this function. In other words, it's the Laplace transform of this function. So that's really all there is to the shifting theorem. But what it says, once again, is if you know the Laplace transform of a function, little f, then if you multiply little f by an exponential e to the at, the Laplace transform of that product will be the same capital F you had, but a horizontal shift. There's a nice little consequence we can state using the shifting theorem that we just derived. We already computed that if f of t is 1, its Laplace transform capital F of s is 1 over s. We also, however, computed that if g of t is e to the at, its Laplace transform is 1 over s minus a. But the second result is just a shifting theorem application of the first. If capital F of s is 1 over s, then what's capital F of s minus a? It's 1 over s minus a. But since capital F is the Laplace transform of 1, it follows that capital F of s minus a must be the Laplace transform of e to the at times f of t. F of t was 1, so that's just e to the at, which was g of t. In other words, having found the Laplace transform of 1, we can apply the shifting theorem and immediately find the Laplace transform of e to the at times 1. Now, online, in any differential equations book, you can very easily find tables of Laplace transforms for many, many basic functions. What's the Laplace transform of t? What's the Laplace transform of t squared? What's the Laplace transform of sine t, etc., etc. So just like there's tables of derivatives and tables of integrals in calculus books, there's tables of Laplace transforms in differential equations books. And just searching online, you can find hundreds of them. We're not really going to give a specific table here in these lectures. It's assumed that you can find one and you'll have one nearby. Much like you probably have a table of integrals that you refer to often, it's assumed that you can just find a table of Laplace transforms to refer to on your own. So from this point forward, we're really not going to be computing Laplace transforms of any elementary functions that you could definitely find the Laplace transform of in a table. Okay, so the products or sums of powers of t, exponentials, sines, cosines, all of these will be in any table of Laplace transforms, so we are not going to bother to figure them out. Altogether, what have we discussed? The Laplace transform is defined as an improper integral. For a function f of t, we denote its Laplace transform as capital F of s. Note this is a new variable. So we always change the variable of the function. This is a very necessary change if you actually work through the definition of the improper integral. You need two separate variables in there. The first shifting theorem, the one we discussed in this video, gives an immediate way to find the Laplace transform of any exponential e to the at times little f of t if you already know the Laplace transform of f of t. Also, tables of Laplace transforms are very easy to find, and from this point forward, we assume you have one nearby.